Yeah, hi everyone, and thank you, Sasha, for the nice introduction, and thank you for inviting me to this online seminar here and also to the organization team. As you mentioned, I will talk a bit about general plate kinematics and reconstructions in the Northeast Atlantic, as well as existing models. And at the end, I would like to show you a recent approach that I developed together with my colleagues Christian Berndt, Mansour Abdelmalak, Grace Shepard, and Jan-Inge Verleide. Okay, first a few words on the tectonic structure or the tectonic setting in this study area. So the Northeast Atlantic is a rather young ocean that opened roughly 55 million years ago. And as you can see in this image, in the image over there, with my pointer here, there are like very prominent ridge segments, which are the Reykjanes ridge here in the southern part of Iceland that connects north to the Kolbeinsey ridge. Then we have even more north the Mons ridge and the extinct Egge ridge over here. The most prominent fracture zone is the Jan Mayen fracture zone, which is indicated with this abbreviation over here. So even though we have clear ridge segments, plate tectonic modeling in this area is complex due to several factors, which I would like to point out over here. So first of all, there's a plume in the center of the region. So it's the Iceland plume that contributed to some extent that the North and East Atlantic was opened. As well, there is a microcontinent involved, the Jan Mayen microcontinent, which sits now where the label is in the middle of the ocean. As well, we have an extinct ridge over here, the Egge ridge, which was extincted about 30 million years ago. We have transtensional breakup in the north, where Svalbard is located. And three other parts. So we have, if we look at the crustal structure, especially we have underplating, highly stretched crust, especially in the southern part over here, and rift jumps. So that makes plate tectonic modeling quite complex because effects might be also overlapping. But in general, especially with regard to underplating and highly stretched crust, so this is a classic example for a volcanic type of passive margins. So the question is now, why do we actually need a good knowledge about plate kinematics in the Northeast Atlantic? There are several reasons, but one of the most prominent is that if we look at the breakup, because we know that the breakup was characterized by a huge amount of magnetic material that was in place during a very short time. And then a lot of discussion is going on how this magnetic material was placed. Anomalous hot and or a fertile mantle plays a big role for that. So this large amount of magnetic material caused also environmental perturbations. So what happened after this huge amount of magma was in place, that greenhouse gas emissions caused magmatic degassing, and this had consequences on short and long-term temperature changes, and the most prominent is the PETM, so Paleocene Eocene thermal maximum. So clearly, magma emplacement has effect on past climate. The controlling factors of volume distribution and especially the timing, which is relevant for plate tectonic reconstruction of this modeling, of this magmatism during continental rifting, this is still unknown. And a proper plate tectonic model helps to constrain the timing of the breakup. So how can we construct such a plate tectonic model? First, it makes sense to investigate the younger tectonic history, and then we need to have a look into oceanic lithosphere. So this is a general sketch over here, where we have the typical features of oceanic lithosphere, so magnetic stripe patterns, which are caused by polarity reversals, as indicated here. Now we can pick and date these reversals, then we get magnetic chromes, and this is an example profile across the ridge over here. And when we have a look in the magnetic intensity, we can pick the peaks in this intensity and correlate them to certain times. And if we combine such a profile, or if we have several such profiles, we not only have one magnetic bone, but we have a line of magnetic isochrones, which corresponds to the same age of oceanic lithosphere. Now, for a plate tectonic model, we would need to not only to combine them, but to rotate them. And this is shown in this panel on the right, top right over here. And what you see is also, that's an example for the Northeast Atlantic. When we have identified some peaks over here of magnetic intensity, we need to rotate the intensity of one tectonic plate to a fixed another one. So in that example, Eurasia would be the fixed plate, and then North America or Greenland would be the rotated plate where we want to rotate this magnetic peak to the other side. And this amount of rotation that always corresponds to an Euler pole, and this is defined in this panel over here. So an Euler pole describes how plates move on a sphere. So how does this look now for the Northeast Atlantic? In this area, a series of global and regional plate reconstruction models have been published over the last 10 to 15 years. And in the animation, which I'll show you in a few seconds, that's derived by a combination of several of these studies. And if I now go back in time, you can have a look at these two ridge segments over here. So what you can see is for the Koblenzer ridge and for the Mons ridge, the information of magnetic isochrones works pretty well. So you can see that no chrones are overlapping, and the closure in that case works pretty well. If I run this once more and you have maybe a look at this agar ridge part over here, you can see that it works not perfectly everywhere. Especially if we have a look at the agar ridge, you see that there's a huge overlap of magnetic isochrones, especially in this part over here. And also this region is, we don't have a good database, and currently plate tectonic model not precisely image this closure of the ocean in that part. So what we like to get is something like this. We like pull, if we keep Eurasia fixed, we like to pull Greenland a bit more back to get rid of this overlap over here. So one observation we have already is that existing plate models suggest that first, the fit of the magnetic chrones in the agar ridge system is too tight, as we saw by this overlap. But as you might have seen before, there is also the movement of the tectonic plates before oceanic lithosphere was created. And that this kind of movement basically reflects stretching of the crust before rifting occurred in this area. So we also learned from existing plate tectonic models that the crust was stretched before continental breakup occurred. And this is the part that I would like to focus on in the next few minutes. I would like to show you how to use or how to combine information of stretched crust with plate tectonic reconstructions. The best way to quantify the amount of stretching is to use seismic data, or even better, to use interpreted stratigraphy of seismic data. And here I refer to a study by Mansur Abdel Malak et al., which was published 2 years ago in Tectonics. And in this study, they used 8 seismic profiles on each side of the Northeast Atlantic, so conjugate profiles of the Norwegian and the Greenland part. And they nicely showed the crustal structure, and also what they showed, and this is what I want to show you, figure out in the middle sketch over here, that since the Permian, this region not only experienced one rifting event, the rifting that we saw before was only the ultimate result of the breakup, but there are altogether 3 distinct rifting episodes that did not cause any breakup. And this area is very prominent for that, because from the crustal structure, or the interpreted crustal structure, we know that 3 rifting events must have happened before. That allows us to use this information to construct so-called restored COBs, or continent-ocean boundaries, for individual rifting periods. There are different concepts how you can construct such a restored continent-ocean boundary. And in this sketch, I briefly explain how that would work. So the top panel would show us now a present-day crustal structure where we have unstretched crust in the left part over here, and this would be the passive margin or the continuous transition zone. We have different crustal thicknesses and different stretching factors. Now we can set one reference crustal thickness, in that case over here, and then we can compact or de-stretch the crust in a way that this package over here, those two packages, would have the same crustal thickness as to the setting before this rifting occurred. And then we have a distinct restored continental ocean boundary 1 and an extension part over here. So this would be the crustal structure before the first rifting event. And then we can apply this also to now a second event where we would say, okay, here the unstretched crust represents the continental part, and then we need to recalculate basically the crustal thickness to a constant value over here, and then we would have a restored continental ocean boundary at a different place and also a different amount of total extension. So this would be the crustal structure for the second rifting event.
Peter, you are 10 minutes now.
Okay, so people have done this before, and here I show the restored continental ocean boundaries for the Northeast Atlantic. Barnett Moore used it in 2016 and Abdel Malak in 2022. You can see in the study that we have individual information about fugitive extensions on both sides of the margin. And in a study that we did, we used this information plus additional seismic data in the south to construct basically our own across the model by an optimization approach. This optimization approach I just described very briefly, but it's other models before I used basically visual fitting approaches, and we wanted to quantify it based on an optimization which contains some least squares fit of rotated points. And what we then without going too much into detail, what we get at the end is a configuration of, in that case, Greenland relative to Eurasia for each rifting event. So what you see here is in the top panel, the restored and rotated, the restored continental ocean boundaries for the Norwegian side, plus the rotated ones for Greenland in pink. And these are these lines over here. And the value over here corresponds to the Euler pole that is estimated to rotate Greenland to that position over here. And as we have from the seismic data, the distinct rifting events and extensions, we can repeat this procedure for all events over here. And what you see now in the bottom is the corresponding position of Greenland relative to Eurasia if you apply this Euler pole over here. And what you can see if you go back in time is basically the deeper we go back into the Permian, that's the fit between Greenland and Eurasia gets tighter compared to older models, which would be the gray one over here from Barnett Moore. So this is something that we investigated, that we have a more pronounced anti-clockwise rotation over there in this setting. Now we can use this information then to implement the Euler poles into G-Plate's software and to plate tectonic reconstructions. And this is how we would now quantify the rifting. So what we can see here are now not a smooth version of rifting. If I run it once more, but we have now 4 distinct events where crust was stretched. This you see by this step-by-step movement until we have the final breakup and oceanic lithosphere is formed. So to conclude, magnetic chromes in the oceanic lithosphere are the preferred data set to obtain plate reconstruction after rifting and continental breakup. And we have seen that fitting the magnetic chromes in the Northeast Atlantic is challenging, especially for the Egge-rich rift system. These restored continental ocean boundaries, they allow us to obtain the configuration of tectonic plates before or in between rifting events. And we have developed an optimization approach to predict the relative break motion of Greenland versus Eurasia. And the new rotation model captures now individual rifting periods instead of a smooth extension. The pre-Cenozoic fit of the continents is tighter than in previous models. And of course, the predicted plate motions, and this is what we currently are figuring out, they need to be in line with tectonic observations. And with this, I would like to thank you for your attention. And of course, I'm open for questions and for a short discussion.
Excellent. Thanks for this great talk, Peter. We have time for a few questions. If you have one, just put it in the chat or raise your hand and you get the word. And while people type, I have one quick question. How do you deal with magmatic additions in your volume balancing approach? When you add material to the crust, you have to kind of take it out in your reconstruction. How do you assess that? How do you integrate that?
Yeah, good questions. We do assess for this, but it's quite complicated, and it would be like an addition to the sketch over here. This is like a big question that we deal with because it adds another uncertainty. So this kind of figure here, that would represent an ideal case where you exactly know the crystalline thickness of the crystalline crust. But it could be that a certain amount of underplate sits underneath here. And there are areas where we have maybe a good approximation of magmatic underplating. In some areas we do not have. So usually the seismic cross sections over here, they give us an information on how much this magmatic addition might be. But we try to acknowledge this by introducing uncertainties into this, and these uncertainties would then transfer to the restored continental ocean boundary. So we acknowledge this, but we cannot really quantify this amount of underplating over here. We treat it in a way that we would apply this to our code as a kind of uncertainty, which would give a kind of freedom in the fit.
Okay, thanks, Eivind.
Thanks for a very nice presentation. I was wondering, like with the COBs, do you make plate polygons, so like dynamic plate polygons from your results, and also kind of like how this, because this I think this is really great, especially in terms of like reconstructing. If you want to use this for paleo DMs or topography, which I've been working a little bit on. And there's also always a problem with when you just use the polygons, that they are you get like an ocean there because you don't account for the rifting, which you kind of solve here. But does that also, will that change the rest of like a global model? For example, if you move Greenland a little bit, you will also have to move other things.
I 100% agree with this. Yeah, so we are currently focusing here on the Northeast Atlantic, but you might have seen also in the animations at the end that there is something happening in the West as well, and that's not really related yet. But when you change like rotations for two-plate system, you need to be aware that all changing these Euler poles or manipulating these Euler poles will affect the other plates as well, especially when you have a global plate model. So currently, I'm also working on the northwestern part of the Atlantic to get this match there over there as well. But in a very general way, you are right. You would need to consider this for all margins on the globe. The Northeast Atlantic is very dedicated because we have good seismic data, and especially good information about the interpreted stratigraphy over there. But yeah, as I mentioned, in general, in a full model, you would need to apply this to all to as much margin pass as possible.